Well, hello everyone. I'm back, and I'm back to finish up the problem that I left hanging at the end of the Maryland Voss Savant escalator problem. This is actually a seriously difficult word problem from the textbook. We will have harder ones ahead of us, but consider this to be about as tough as you're going to see in any community college math course. Even calculus won't have word problems of this level of difficulty. Now, here is the problem. It says a plane is flying a 2,553-mile trip from Los Angeles to Honolulu into a 60 mile per hour headwind. And it says that the plane's speed in still air is 310 miles per hour. And they ask us to find how far from Los Angeles is the plane's point of no return. In other words, they're asking for a distance. They want to know how far from Los Angeles is this plane's point of no return. Well, obviously the point of no return is a critical idea here, and in fact it's a navigation term that has two meanings. And the second meaning is the one that's apropos to the context we have here, namely a large body of water like an ocean. In that context, the point of no return is the point at which the time forward to Hawaii, in this case, is the same as the time back to Los Angeles. Imagine, if you will, this scenario that you're flying this route and a passenger becomes gravely ill, and you want to know if it's faster to return to Los Angeles or to go forward to Honolulu. Well, the point of no return is the point at which it wouldn't matter if you went forward or back. And so it's this critical idea, and it's nice to see our mathematics get at some really important concepts here. Now, the other idea here is that whenever you have distances and rates, I suggested that you immediately call to mind DIRT, distance equals rate times time. And if you recall from that other video, I said that you want to be able to manipulate that, solve it for R or solve it for T, and that the version of the equation that you decided to use was dependent upon the problem itself, that you would look for the situation where the coming and the going was the same for one of these quantities. If it turned out that time was the same coming and going, you'd use this version. If it turned out the rate was the same coming and going, you'd use this version. And so too with the distance. Now, I haven't ferreted out yet which one of these quantities is the same. We'll get there soon enough. For now though, my next step in solving this, and this is a really vital idea, was to create a little diagram. Strongly suggested that you always do this. Here was pretty much what I created on my paper. I showed Los Angeles, I showed the distance to Honolulu, I drew in a little plane and showed it going against a 60 mile per hour headwind. That right there, that diagram, eliminated 2/3 of the words, and it's the stepping stone, it's a transition to the algebra of the problem. The only parts that it didn't capture were the plane's still speed, the speed in still air at 310 miles per hour, and it didn't answer the question, how far from Los Angeles is the point of no return? Now that idea, the point of no return, I actually played around with it. I wanted to know where it was. And I wondered if it was closer to Los Angeles or to Honolulu. Ultimately, I placed it closer to Honolulu. And here's my reasoning for that. The point of no return is a point at which the time it takes to go forward to Honolulu is the same as the time it takes to go back to Los Angeles. And since going forward to Honolulu is into a headwind, for a given amount of time I'm not going to go as far because I'm fighting that headwind. For the same amount of time, I'm going to go farther to get back to Los Angeles because I'm being boosted by that tailwind. And so that's why I put the point of no return closer to Honolulu. And once I did that, the problem seemed to open for me because, I said there maybe 2 or 3 times, the time going forward is the same as the time going back. And so that answered the question for me. Which one of these 3 cases was I going to use? The time going forward is the same as the time going back. I would use this version of the formula. Now, I want you to take a good look at that because that was the way I constructed my table, that particular ordering of the 3 quantities. And you'll see that when I drag it in here. Here is my table. And we're referencing here the point of no return. From the point of no return, we're going to be going back to Los Angeles International, LAX, or we're going to be going forward to Honolulu International. And so, everything is referencing off of this point, going back to Los Angeles or forward to Honolulu. And from this point is the way we will think about our three columns that we're going to fill here. Now, it turns out that time is going to be the same, going forward, going backwards, or going forward. And believe it or not, this column won't matter in the end. It becomes our hinge point and our actual hack, the idea that we use to crack this thing open. You'll see that as we move on. We need to, though, fill in the distance in the rate columns. And for the rate, let's keep in mind that we're talking about returning to Los Angeles. We know the plane's speed in still air is 310 miles per hour, and we know the plane now has a tailwind of 60 miles per hour. And so that lends itself to this idea of an addition of those two numbers. And that would be the rate if he decides to return to Los Angeles from the point of no return. And similarly, if he continues on and goes forward to Honolulu, then the headwind is going to detract from the speed, and we'll have that quantity. Now I went ahead and crunched those out and use the finished arithmetic as my rates. And so 370 miles per hour is the speed going back, and 250 miles per hour is the speed going on. And now we have to deal with the distance column here. And this is a moment where I decided to do my variable declaration. And I said in the Maryland Voss Savant video that students are reluctant to put up in a place and declare their variables. And I'm reluctant too, but I always try and do it for the main one. And in this case, it's the one we're actually solving for, the distance from Los Angeles International to the point of no return. I'll let x equal that. This is where our focus has to be. This is the answer to the word problem. And so x is going to be the distance from Los Angeles to the point of no return. And the next question is, we now know what this is, it's x. The next question is how do we use x to reference the distance from the point of no return to Honolulu? Well, since the overall distance length of this line is 2,553, if I subtracted out this segment, then I would have this as a remainder. And so that was what I used to finish up this column. And I think that makes good sense. If not, pause the video and puzzle it out on your own. I think you've seen that idea used in many different contexts. And there we go. At this point in time, I felt the problem was done. And I was ready to evoke the hack, essentially. Here again is the idea, the hack, if you will, just a really simple idea. Namely, the time is the same going forward or backwards from the point of no return. And so whatever this number is, I don't know what it is, but whatever it is, both the distance divided by rate back to Los Angeles and the distance divided by rate forward to Honolulu, both of them are equal to it. And so I can just use that as a hinge point and vanish it and say that this distance divided by rate is equal to this distance divided by rate. In other words, this x divided by 370 is the same as 2,553 minus x divided by 250. And we're ready to transition into a mathematical sentence, which looks like this. And the problem is all but done now. This is a simple solve for x, isolate x on one side or the other. And rather than waste your time solving that, I thought I'd let Wolfram Alpha do it and interpret the results because there's something interesting there. Here is the two sides of the equation, and the first thing Wolfram Alpha does is write it pretty for us. And then what it does here is it actually, imagine this, imagine setting this whole thing equal to y. And then in a sense you could say, okay, well if y is equal to all of this, y can equal this part, and you'd get a line, wouldn't you? Or y could equal this part, the right hand half, and you get another line. And that's what you're seeing down here, are these two lines. And these essentially represent, instead of thinking of y is equal to, say, x divided by 370, think of t is equal to x divided by 370. The vertical column here is time, and this is distance, And we are talking about if you were to turn around, let's say at 1,000 miles into your trip, the time back to Los Angeles would be 2 hours and 15 minutes about. Or if you were to continue on from that point to Honolulu, the red, would be about 6 hours and 15 minutes. And of course, this was the critical thing we were trying to find, the point of no return, where turning around and going forward is the same amount of time. Looks like around 4 hours. And so, very interesting thing going on there with the diagram. It essentially captures the idea in pictures. Now here is the actual solution, and of course this doesn't do us much good, and this is the exact form. If you click this button over here, you'll get the approximate form. In other words, the division is a non-terminating, non-ending decimal, and so you'll have to truncate it and approximate it. Let me go ahead and click on that, and here's the division done and rounded. So we're talking about 1,523 miles rounded up to, say, 1,524 miles to the PNR, to the point of no return. And so that is our solution. Here it is right here. And a pretty interesting problem. Very cool. I think one last look at the picture here. And just to be sure we know what's going on here, at someplace around here, you'll reach the point of no return, in other words at 1,524 miles, at which time returning to Los Angeles will take the same amount of time as going forward to Honolulu. If a passenger became gravely ill, say in here someplace, you'd want to turn back. Or if a passenger became ill here, you'd obviously want to continue on to Honolulu. So, interesting mathematics. I hope this helped. I'll be talking to you again soon.